All right, so thank you so much for the invitation, and thank the organizers. What I'm going to talk about is actually a rather technical mathematical result. I will not go into details, of course, and instead, what I will try to do is to point out features of point vortices models that might be useful to describe, to model complicated phenomena like features of turbulence, boundary layers, effects, and stuff like that. And two references to begin with. So yeah, the main one is this paper by myself and Umberto Pareto. But for more complete references on point vortex dynamics, I refer you to the to this big work of Asanaref that covers the whole history of this model, which dates back to the 19th century actually. And yes, of course, then literature is extensive, and so if you go through the references in both works, you can kind of get a picture of the topic. What is okay? All right, so the PDE model from which everything comes from is the following. It is this generalization, if you want, of the two-dimensional Euler equation. So you have usual advection of a scalar, which is the vorticity, and the vector field that drives it is given in terms of the vorticity omega in the following form. Alpha here plays a quite a different role from the one in the talk of Benedetta, of course. So what happens here? If you take alpha equal 2, then this is the green function of the Laplacian, and so you're back to two-dimensional Euler equations. If alpha is equal to 1, then this becomes the surface quasi-isotropic equations, which is an interesting model, and it is usually proposed as a toy model because of 3D Euler equation, because it shares with it some features. But then more generally, you can take alpha in the interval 0 to 3, and what happens towards 3 is that the interaction becomes less and less important. And so in the end, no, yes, maybe this I will discuss later. Anyways, this is the range of parameters I will consider. And to these PDEs, you can add many features. The first one is the geometry of the domain in which you consider them. So yeah, for what I'm concerned with today, you can think of it on the whole plane, but then you can go to smooth bounded domains, so to study boundary effects, the periodic two-dimensional torus, but also the sphere, and then you can add more effects, external fields, or the rotation of the sphere. These are small generalization that can be implemented in the discussion of today's. And right, so what are point vortices? If we take a initial distribution of the vorticity, which is a scalar field, concentrated in finitely many points, so a weighted sum of Dirac deltas, then one can ask what is the evolution of this, and you know, the PDs doesn't really make sense, but then one can take smooth approximations of these Dirac deltas, run the PD, and then send the approximation to the limit, and what is obtained is this kind of dynamics. So one has a finite number of points, on which vorticity is concentrated. Each of the points has its own intensity, and the points will move under the influence of the other points according to this ODE system. And this ODE system is actually singular. You can see that it is singular because, of course, because of the kernel that produces the velocity field from the vorticity. And you can see here, the singularity happens when two or more of the vortices of these points collide, go to the same position. And yeah, so the first thing to mention is that you can actually prove that for almost all initial conditions, this does not happen. So for almost all initial conditions, the system is well posed. You can run it for all times, and the solution is smooth. But this does not mean that collisions are not possible, and instead it is what I'm going to talk about. All right, so quickly on the relation between the ODE system and the starting PDE. A good way to think of this link is the following: if you take the PDE and write it in a weak form, so you couple with a test function, a small bump, and you write the weak formulation of the PDE, you can then take a solution of the point vortex dynamics, take as the vorticity the empirical measure of the vortices, and this omega t will solve the weak formulation, provided that we neglect diagonal contribution. What is the diagonal contribution? Well, this is double integral. Omega here appears twice, and so in this double integral, when one takes the product of omega with itself, there are times in which the vortex appears twice, and so this would mean that you have to evaluate this kernel at the same point, and you cannot do that, right? Because it is divergent on the diagonal, so you have to neglect the diagonal contribution, and this actually makes sense. Looking back at the ODE system, the vortex J does not interact with the vortex K, and this is reflected in this fact, in the fact that you have to neglect the diagonal contribution, and you can motivate it, as I was saying, taking limits of smooth solutions of the PDE. All right, so the ODE system is actually integrable in the Hamiltonian system. It is a Hamiltonian system. It is integrable in the case of three vortices. As soon as n is bigger than 4, it is not integrable anymore. And this is part of the reason why the system is so interesting, because it is not mixing or ergodic at all. It has many conserved quantities, but it is not integral. So many interesting things can happen. But when n is equal to 3, one can integrate the system, and one can see that if you properly choose the initial condition, you can make three vortices collide, and they will collide in a self-similar way. So the picture here explains it. If you take three vortices, you put them properly with proper intensities, you can choose them so that in finite time they will go to the same position, and this will cause a singularity to appear. You cannot extend the solution anymore, because in the ODE everything now is infinity. Right, so this is an explicit form of the self-similar collapse, and I mean the precise expression is not really important for us now. It was just to show you that you can actually write a formula in this n equal 3 case. Notice that collapse can only happen in self-similar form for alpha equal 2 in the Euler case, for other values of the parameter, there can be other kind of collapses. And yes, and also a further remark, which also goes back to the title. I'm talking about collapses. I'm talking about vortices that go to the same position. But thanks to the symmetry of the system, if you reverse time and change intensities, you can transform the collapse into a burst of 3 vortices out of a single one, like looking at this formula. But this is also true like for a general system of n vortices. There are other symmetries you can exploit to transform collapses into bursts, but I mean this is the easiest one to picture. Right. So what happens after the collapse? This is actually a big question, and one can imagine that the evolution goes on in different ways. So the first, perhaps the naive one, would be that vortices merge into a single one that stays still from now on. The intensity will be the sum of previous intensities. They simply are stuck together from now on. But yeah, you know, reversing time, as I told you, you can also put together a collapsing solution and a bursting one, and provided that the total intensity is the same, you can call this a solution. And why I'm calling it a solution of what? Well, not of the ODE system because it is singular, but it still satisfies the weak formulation of the PDE. So from the point of view of the weak formulation, this might be regarded as a measure valued solution. And yeah, so the possibility of splitting, of bursting vortices or making them collide, at least for 3 vortices, tells us that weak solutions, measure value solutions of the PDE in this sense are extremely unique, because you can consider a solution where 3 vortices collide, then merge them for a finite amount of time, and then make them burst again, and this will be a solution, but of course arbitrary non-uniqueness. So yeah, so the question of what is the physically correct evolution is actually an open problem. You can try to smooth the interaction kernel, and there are some results with very precise smoothings, but I mean nothing complete. So this remains quite open. And so my main result is the following. At least when alpha is equal to 1 and 2, so in the Euler case and in the surface quasi-geostrophic case, you can do the same of the 3 vortices case on arbitrarily large configurations. So yeah, so you take any configuration of n distinct vortices, and then you can find a solution of the ODE system in a small time interval with extreme open, that instead has n plus 2 vortices, where 3 vortices have bursted out of a single one. And right, so this tells you that yeah, you can take any configuration and you can burst one vortex, and then you can reverse time, as I told you, so you can actually produce arbitrarily large configuration of vortices in which 3 of them collapse at finite time, and play around, paste this kind of solutions and use non-uniqueness and construct wild thing. And right, so this also holding all the geometries, and I will give you a hint on why this is true in a minute. So why am I claiming that this kind of phenomena might be interesting or useful? Well, right. So on one hand, of course, because of abstract properties of this system that appears quite naturally, but also because of the following things. So right, let us keep thinking about this kind of vortex evolution as measure valued solutions of the PDE. So you can look at the velocity field generated by these vortices. It happens like this. Yeah. So right. So take vortex configuration. You take it as a vorticity distribution, and then this formula will give you the velocity field generated by it. And actually, the energy, as it is usually defined, of this velocity field diverges. It is infinity. You can prove it with a very simple integration by part. And this is because, once again, we have to deal with self-interactions of vortices. So instead of the usual energy, one should consider the Hamiltonian of the ODE system. So yeah, I mentioned it. The ODE system is a Hamiltonian, and this is the Hamiltonian function. And yeah, and you can see that here I am not putting the equal sign, right? So here, a couple of vortices are all distinct. And right, so this is the Hamiltonian function. This is preserved by the ODE system, and writing the Hamiltonian function, one could start to think at all the statistical mechanics one can do with the system, and this is also a big topic, but let me just mention it like this. All right, so back to our splitting and births. So looking at the Hamiltonian function, what happens is that if you merge vortices after a collapse, what happens is that you are preserving the total intensity, the total vorticity of in the dynamics, but this energy, the Hamiltonian, is decreasing. And right, so this tells you that you are actually able to produce this kind of weak solutions of measure valued solutions of the PD, in which you decrease energy. And another thing you can do is to randomize times of splitting. So you let the point vortex evolution run, and at some random point you split one of the vortices, because you're always allowed to do so because of the theorem. And so this produces a Markov process whose trajectories solve in a weak sense this PDE, and bursting vortices will increase energy instead of decreasing it. How much time do?
About 3-4 minutes, 5 minutes.
Great. So in the previous slide, I didn't write it, but I mean, I was still assuming that alpha is either 1 or 2, because those are the values for which the theorem holds right now. What about the other values of alpha? Can one repeat this construction for other values of alpha? And to try to understand what happens, I have to give you a small bit of an idea of how the proof works. So I think it is rather natural to believe that everything boils down to understand what happens to the system of 3 vortices. Right, so take maybe I should have written. You take 3 vortices, you take the ODE dynamics, and you add a external crossing term. And if you are able to understand what happens in this case, you are basically able to do everything I told you, because in a large system of n vortices, what you do is focus on a single vortex. You want to split it, and so you look very closely at it and regard the influence of all the other vortices as an external field. But this also deals with different geometries, right? If you have a boundary, you take a look at one vertex, you want to split it. You have to ensure that you start a bit far away from the boundary, but then the influence of the boundary is just an external force, right? And right, so you just have to see that you can burst a vortex into 3 ones, or conversely find a configuration of 3 vortices collapsing into a single one under suitable external forces. And yeah, so and the idea, of course, is more complicated than that, but the core of the idea is to set up a fixed point problem in terms of suitable coordinates. So you introduce good coordinates that center around the self-similar solution, because you expect to be close, at least for small times, to the self-similar solution you are able to produce explicitly in the funny case. And so you set up these coordinates, and then you linearize the ODE system around the self-similar solution. And you can see that this kind of coordinate measures how close you are to the self-similar solution, because right, so the z's were position of vortices, the notation is complex, and so if A1 and A2 were the positions from where the 3 self-similar collapse started, well, this ratio should be closer to this ratio if you are close to the self-similar solution. Right, so you linearize, and then you have a linear system, big linear system, and you are reduced to study eigenvalues of the matrix of this system. So for alpha equals 1 and 2, it turns out that this matrix has a nice behavior. It has eigenvalues with a real part minus a, and minus a was a parameter in the self-similar evolution ruling the speed of which at which you are going to the collapse point. This is still true in a small interval around the parameters 1 and 2, Euler and surface quasi-geostrophic. As soon as you go out, well, first real parts of the eigenvalues still are negative, but you do not have a good control on it, and so you are not able to conclude the proof, to set up the fixed point problem. Going close to 0 or 3, everything is spoiled. So eigenvalues start to have positive real part, and you can do nothing, which is rather peculiar, I guess, because going close to 0, what happens is that the interaction becomes more and more singular. So so here instability might be expected, right? So you expect the system to be more and more unstable going close to 0. But when alpha approaches 3, what happens is that the interaction between vortices does not depend anymore on their distance. And so in principle, the system should be more stable, at least intuitively, but it turns out that no, looking at this kind of linearization, this is not the case. And so, yeah, so why this is the case remains to be understood, and this is a good moment to stop. Thanks.
Thank you very much. We have time for questions. Your hands went up at exactly the same time, Simon. Please go ahead.
Thank you for a very nice talk. You said that the result will work so in any domain. So if you are on a compact domain, a torus or a sphere, yeah, when the vortices burst, what happens?
Well, at small time, they burst out of a single one, and then right, so on the torus they will travel around the torus, and I think it is not so easy to rule out a collision at a faraway time, because you can control pretty well what happens at small times, but then as time goes on, yes, in principle they might collide. Yeah, and this is yes, this is a subtle question actually. So the statement I showed you at the beginning, the fact that for almost all initial conditions, collisions do not happen, tells you very, very little about the system, in sight of all the discussion that followed, because taking a look at the technical proof, you can actually say that the set of configurations leading to collapse has codimension 1, so it is rather large. You have freedom to make them collapse. And so yes, and yeah, right. Your question is insightful, because also thinking about the Markov process construction that postulates that vortices split at random subsequent times. Well, you should in principle take care of the possibility that they might collide with each other, especially when there's many of them. But on the other hand, if you are looking at this as weak solution, you can accept that if they collide, they are put together, and so it is a rather arbitrary construction. And like there are some works that try to numerically simulate this kind of constructions, and so you can explore numerically, but theoretically it is quite hard.
Willem.
Okay, I'm not an expert in this area. I'm just curious. So the vortex point methods are introduced mostly as a numerical method, and people are mainly interested in the limit when there's an infinitely many particles.
Yes.
And what I know, the little I can remember from these methods is that for Euler equations at least, they don't converge, they don't behave well. So that's why people introduce what's known as the vortex blob methods.
Yes.
The question
which
is,
would be the approximation I was talking about when motivating.
okay. So my question is, have you looked at the infinitely many particle case, and well, especially interested in the case of SQG?
Right. So
behave better.
you can. Right, so there are many ways to take infinite particle limit. A simple way to do so, and perhaps it is not what you are asking, is a mean field limit. So you take infinitely, more and more vortices, like going to infinity, but you scale the intensities, and right, and you scale them as right, so xi i's were the intensities, and you scale them divided by n, and right, so and this converges to, like in the case of Euler equation, converges to a stationary solution of Euler equation. But this is also true in the surface quasi-geostrophic and more general alphas, and you can refer to a work of Marco Romito and Karina Geldhauser, in which they start this mean field limit. Simply sending n to infinity without scaling, I do not know. I do not know. Yes, so from without, right, so without scaling intensities, you have divergent objects, and so maybe let me try to rephrase. So you're wondering what happens to the system when n goes to infinity, and you look at the system.
So people looked at this problem, but at least for Euler equations, but I have no idea whether
Yes,
the SQG case was addressed.
yeah, it depends on what you are trying to see, like from I mean, in order not to say incorrect things, I
You can
will
look at the work
just
of Troy.
yes. That is the famous
Yeah.
approximation method. Yeah. And
Shall we leave this for later and probably take a quick question? And
yeah, sure.
yeah, I'm sorry because there's
No, it is true. And also I should just refer to this because I cannot provide a good answer further than this. So.
I don't want to cut off any discussion, but there are maybe other questions. If that's not the case, then let's thank Francesco Grotto.